Welcome, ladies and gentlemen, to our lecture on work and kinetic energy. So let's start our consideration of energy by thinking about something different for a second. Let's think about something that we considered briefly before that we didn't really look in depth at, okay? So let's consider a spring. Remember that we learned Hooke's law to express the force that a string will apply when it's compressed or stretched. But remember that the force is proportional to the distance that the spring is compressed at all times. So when I compress the spring this far, I get some force. And when I compress it this far, I get some different force. Okay? And when I let it go from one of these compressions, at every point along the way, as it stretches back out to its equilibrium point, I have a new force, right? So after I let it go, the force is always changing. So if I wanted to know, for example, how fast the spring would propel a block when I let it go, say, what if I had like a spring-powered Nerf gun or something like that, and I wanted to make sure it was safe for kids, so I need to know how fast it's going to shoot the little Nerf balls, right? And then when I pick the spring, I have to pick a spring that'll shoot a Nerf ball fast enough that the little gun can be fun, but slow enough that nobody gets hurt. This is a really hard problem to solve using the tools that we've learned so far, because we solve for things that have constant net forces and therefore constant accelerations. This is the exact opposite. The net force is always changing, and so the acceleration is always changing. This kind of difficulty motivates us to look more closely at the physical world and come up with a new method for predicting the behavior of the objects around us. So let me introduce the concept of work. In physics, we do work on something when we move it. So in particular, we calculate this quantity work by calculating the dot product between the force that's applied and the displacement that we impart on the object. So, finally, after I've been making you guys do a dot product on every homework, here they are. We come to our use of the dot product, okay? Now recall that with a dot product, we always get a scalar quantity, okay? So we input these vectors, but what we get out is a scalar, okay? Indeed, this equation was incorrectly written. Work is not a vector, okay? Work is a scalar because it's a dot product of force and displacement. So note that even when we set up a coordinate system with orthogonal coordinates, like we have for every problem so far, this equation does not represent a system of equations, okay? There's always just one equation that returns the scalar quantity work. So if we take our favorite example where I push a car, okay? We have this car sitting here and I push on it with some force. The work that I do on the car is the dot product of the force that I push on the car with and the displacement that the car undergoes. So if I push the car some distance, x, this displacement and this force are used to calculate the work, okay? The work in this case is Fpx, okay? No longer vectors. In this case, it's just the magnitude of these two things multiplied together because the force and the displacement are in the same direction, okay? This x-hat direction. But now if I push on the force, or if I push on the car with a force that's pointed like this, okay? So maybe I'm hunched down back here and I'm pushing the car with my back and I'm kind of pushing up and forward on it. The work that I do isn't just the product of the magnitude of the force and the displacement, because now they're not pointed in the same direction. So then we'll call this FP2. With FP2, you can see the direction of the displacement is this x hat. It's this direction here that our first force was in. So FP2.x is FP2 x cos theta, okay? It's the dot product. So when I go to apply a force to something and it moves, only the component of the force that's in the direction of the displacement does work. The other component of the force, in this case the component of the force that points this way, right, FP2y, that component does not do work. So this idea of work is what we do with forces. As these different forces move things around in the world, the different forces are all doing work on the different moving objects that we see. And note that work, when it's done, can be positive when the force points in the direction that has the same component along the displacement, okay? Sorry, that has some component along the displacement. So let's erase this and look again at this. So we have our car again. And it goes through some displacement, x, okay? And x points in this direction. Okay, and we'll make that our x hat direction. You can see that if I push with a force in the same direction, we said that the work, which is the dot product of the force of the push and the displacement, equals FPX. Okay? And this is because it would actually equal FPX cos theta, like we were learning about with our dot products. But this theta between them is 0, right? And cos 0 equals 1. Okay? So we end up with just FP times X. But now if I change this and I make FP point in the other direction, then this cos theta is cos 180 instead of cos 0, right? And that's minus 1. So if the car is displaced in this direction here, in the x hat direction, but my push was against that, then I have the direction of displacement and I have the direction of the push, and this angle between them, theta, equals 180 degrees. And what that means is that instead of getting the work is equal to FPX, it's equal to minus FPX. Okay? So I can do negative work on an object when I'm opposing the motion of the object. Okay? Now it seems funny to say that I push on the car and it moves in the opposite direction of my push, but it's actually not such an odd situation. You can actually imagine that if the car were rolling for some reason, okay, and I wanted to stop it and didn't have time to get in it, I might just push on the front of it, right? So it's already rolling, and then I come up to it and I push on the front of it backwards, and I do negative work. So now let's think for a second about pushing a block for some distance x, okay? So I have this block, It's sitting on some surface, and I push it some distance x. In the beginning, it has some velocity v naught, okay? Now, this might be 0, but then again, it might not be 0. Maybe the block was already sliding, and then I pushed it some distance x, okay? And it has some velocity v final. We know from our kinematics that v final equals v naught plus at. And we can manipulate that algebraically and say that t equals v final minus v naught over a. And then we also know that x will equal, let's say I choose my coordinate system so that x naught is 0. I would still have v naught t plus 1/2 a t squared. But if I plug in this expression that I have for t, I get that x equals v naught times vf minus v naught over a plus 1/2 a vf minus v naught over a squared. And now let's be really explicit here and mention we're doing this in the x hat direction, where x hat is this horizontal direction, okay? So all of this is occurring in this x direction. And we have our equation up here. And let's just do a little algebra on it. So we have vf v naught over a minus v naught squared over a plus vf squared over 2a plus v naught squared over 2a minus vf v naught over a. Okay? So all we did is expand this, okay, and this. And we have all these terms. And we notice that we have a plus vf v naught a here and a minus vf v naught a here, which means that these two terms will cancel. We have a minus v naught a here and a plus 1/2 v naught a here. Okay? So what we'll end up with is v final squared over 2a minus v naught squared over 2a. And then if I wanted to solve for a, if this is x, what I would end up with is that a equals vf squared minus v naught squared over 2x. So now what we have is this constant acceleration that we're creating by having this constant net force, right? So net force in the x direction is equal to the mass of this block times its acceleration, which is equal to the mass times this expression that we have for the acceleration, but then if I bring the x over to the left, you'll see that what I end up with is a net force, okay? So, in fact, let me write this differently, just so it's a little more clear what we're doing here. Instead of the sum of the forces in the x, we're going to write F net, okay? The net force in this direction times x equals, and then I'm just going to pull these two terms apart, okay? I'm going to let each of them be their own term. So it's 1/2 m vf squared minus 1/2 m v naught squared. And notice what we have over here is work, okay? Now, by taking the x components, we've already done the dot product, right? The displacement was in the x, and then we just concerned ourselves with the net forces in the x direction. So we've already done the work of making sure that we're only considering the components that are pointed in the same direction as the displacement. Okay? So this is work, and it's equal to this stuff over here. Okay? So this quantity, 1/2 mv squared. This is called kinetic energy. This is the kinetic energy of the object. And note that this is a scalar quantity. So unlike the force, the velocity, the acceleration, any of those other things that we talked about before, the kinetic energy doesn't depend upon the direction the object is moving. Okay? It's just a magnitude. We see that we have a mass, which will always be positive, and we have the velocity squared, which will always be positive because it's squared. So the kinetic energy is always greater than or equal to 0. Okay? And it can only be equal to 0 if the object has no velocity, right? If the object is sitting still. Because the mass of some object is always going to be greater than 0. And then note that what we have in this equation up here is a final velocity minus an initial velocity. Sorry, a final kinetic energy minus an initial kinetic energy. So what we have in this equation is a change. In kinetic energy. So just like displacement was x final minus x initial, and that was the change in position, this equation is kinetic energy final minus kinetic energy initial, which is the change in the kinetic energy. So this equation, if I replace this F net x with W, because this is work, this equation is an equation called the work energy theorem. And the work energy theorem says that the total work done on an object is equal to the change in kinetic energy, okay? Where kinetic energy is this 1/2 mv squared for the object. So now when we go back to pushing on the car, remember that when I was pushing on it in the same direction it was moving, that made work positive. And indeed, in that situation, if I have, say, a car at rest, when I push it this way and it moves this way, I increase its velocity, right? I'm giving it some acceleration. And I end up with work that's positive. The kinetic energy at the end is bigger than the kinetic energy at the beginning. And then remember, when I push in the opposite direction, so the car's already moving and I push it back this way, well, why do I do that? I do that to slow it down, right? I do that to maybe stop the car. In that case, the final kinetic energy, because this V will change, the final kinetic energy is going to be smaller than the initial kinetic energy. And indeed, that gives us a situation where the work that's done is negative, okay? The car loses kinetic energy. So note also here that the work energy theorem, it was using the net force that was in the direction of the displacement, okay? So when I did this example, I never actually said if this surface was frictionless or had friction. And this work was equal to F net x, okay? So with friction, W would equal the force of my push minus kinetic friction while I was pushing it, right? And that would be multiplied by x. Whatever that net force is would be multiplied by the displacement that I gave the block. If it was without friction, then of course W would just equal the force of my push times the displacement that I gave the block, right? So this F net, it might not be just one force, okay? There might be multiple. But the net product of all the forces on the block, if I move it some displacement, there must be a net force that let me move it that displacement, okay? So there's something that I put in here. It may have multiple terms, like our example on the block here, with and without, or with friction, or it may have just one term, like this example here when we move the block without friction. But I can use this net force times the displacement to get the work, and then I can use this work energy theorem to find the change in the kinetic energy of the object. Okay? So we have this quantity, kinetic energy. And as we usually do when I introduce a new quantity, let's look at the units on it. So the units are K as units of kilogram, meters squared, per second squared. But remember that a Newton was a kilogram meter per second squared. So this is actually newtons times, let's not put a dot product, times meter. Okay? And this unit is called the joule. The joule is the SI unit of energy. Okay? So what is kinetic energy? Kinetic energy is the energy of motion. So it's equivalent to the total work needed to bring the object to that speed. Or, another way to think about it, is it's equivalent to the amount of work that an object can do before it comes to rest. Or, another way to think about it, it's the amount of work that it would take to bring the object to rest. Okay? So if I have some kinetic energy, 1/2 mv squared, then the work that it would take to bring me to rest, if I have this energy, is going to be 1/2 mv final squared, which would be 0, right? Because v final would be 0, minus 1/2 mv squared. This kinetic energy that I have, okay? So the magnitude of the kinetic energy I have is the same magnitude of the work that it would take to bring me to rest. I have the opposite sign here because work to reduce kinetic energy is always going to be negative work. So the idea of kinetic energy, we just kind of used Newton's laws to derive kinetic energy and the work energy theorem. So it's only useful in inertial reference frames, okay? It doesn't work the same in accelerated reference frames. And also note that because speed is in our expression, the kinetic energy can change depending on the reference frame that you choose, okay? But the work energy theorem will be true within each individual inertial reference frame that you choose. So you can imagine if I was calculating my kinetic energy and say I was on a train car. In the train car, if I was pushing a block, okay, and I gave that block some speed in the train car, v, that would require a certain amount of work, okay, to produce the kinetic energy that I gave the block. But the kinetic energy would be based on v. So if I'm comparing to the inside of the train car, and the train car is going at a constant velocity, if the train car is accelerating, this actually won't work, because then our inertial reference frames that were required for Newtonian mechanics to derive this, well, they won't hold, okay? So if the train's going along at a constant velocity, if I compare the speed of the block to the train car, if the train car is my inertial frame of reference, I'll have one speed. But if somebody was standing out here on the side watching the train go by, they would see a bigger speed, right? The relative speed of the block would be the block moving in the train car plus the speed of the train car as it goes by, right? So they would come up with a different kinetic energy for the block. This example shows us the kinetic energy is dependent upon reference frame. But regardless of the reference frame chosen, the work energy theorem will work as long as we stay in that reference frame. So if the person watching from outside of the train used the work energy theorem to calculate the work done on the block, they would still be able to find the work done on the block. If the person inside the train wanted to calculate the work on the block, the work energy theorem would hold in here too. In each inertial reference frame, as long as we don't mix terms from the two different reference frames, the work energy theorem will work. Okay? The work energy theorem is correct. So now I want to think about kinetic energy for a second by thinking about an example. Okay? So let's think about kinetic energy and the work energy theorem by thinking about an egg toss. If anybody's ever done an egg toss, the goal is to toss an egg back and forth, and each time you toss it to your partner and they catch it and the egg doesn't break, you each take a step back and you keep getting further and further apart, with the goal to be to get as far apart as you can from your partner, throwing the egg back and forth without breaking it. Okay? So we know that if I put a force on the shell of an egg, if I put too much force on it, the eggshell breaks, right? So I have some F max that the shell can handle without breaking. Okay? So much like the static force of friction, the eggshell can apply a normal force back on my hand up to a certain point. If I go beyond that point, then what happens is I break the eggshell, okay? Static friction can apply a force up to a certain point, and if you go beyond that point, the object moves, right? You no longer have static friction. The normal force from the eggshell is the same way. The structural integrity of the egg can only push back against a force up to a certain point. So if I'm doing this egg toss, what I want to do is throw the egg back and forth without ever applying a force that's greater than what the eggshell can handle, right? So when I go to catch the egg, it has some speed. And the speed, of course, is going to be greater as we throw the egg further and further back and forth, right? So this requires some set amount of work equal to the egg's kinetic energy. The egg's kinetic energy is 1/2 mv squared, and these are all well defined, right? The egg has a specific mass, and when I go to catch it, it has some specific velocity. Now it's different for each throw, but on any one given throw, when I go to catch the egg, it has a specific amount of kinetic energy. And catching the egg means reducing that kinetic energy to 0, right? I need to stop the egg from moving in my hand. So that means that I must apply a force to the egg, right? Because if I want to change the kinetic energy to 0, I need to do work on the egg, which means applying a force over some distance to remove the egg's kinetic energy, okay? But we know, again, if I press on the eggshell too hard, I'm going to break the eggshell, okay? But I notice that the work, right, I have to do work to reduce the kinetic energy. And the work is the force times the distance. So what do I do when I go to catch an egg in an egg toss to catch it without breaking the egg? I have a specific amount of work that must be done, but that doesn't mean I have to apply a specific force, right? So if I extend this x, if I make x bigger, I can make F smaller and still do the same amount of work, right? So when I go to catch the egg in the egg toss, what I end up doing is I reach my hand out, and then as the egg is hitting it, I try to move my hand along with the egg as I catch it so that I stretch out the distance that I'm applying the force, right? And if I do this correctly, then I can apply a much smaller force to the egg over a much longer distance, and I can catch the egg without breaking the shell, okay? If I just stick my hand out, when the egg hits my hand, the kinetic energy goes from whatever it is, from this quantity, to 0 over barely any distance at all, right? My hand barely even moves when the egg hits it. When that happens, the force that I have to apply to do the work to change the egg from having this kinetic energy to having no kinetic energy is really big, okay? I have to apply a really big force over a distance of nearly 0 to stop the egg if I'm not moving my hand, right? So moving my hand along with the egg allows me to keep the force applied to the egg below the breaking point for the shell while still doing the amount of work that's required to catch the egg. The amount of work to change the kinetic energy of the egg from whatever it is while it's flying through the air to 0. So the work energy theorem and kinetic energy are interesting concepts, but when we derived this, we were still looking at a constant force. And remember that I started this whole lecture by using a spring to illustrate a problem with Newton's laws in describing behaviors with constantly changing forces, right? So we did all this talking now, but are we actually in a spot that's any better for looking at these systems with changing forces? So when we think about systems with changing forces, there are a lot of different systems we could think about. One is, remember we've been looking at ramps in a number of cases, right? Blocks sliding down ramps, Jim Bob going off ramps, all kinds of ramps, right? And we've always drawn them like this. But if you've ever seen a real ramp, or a half pipe or something like that, it's pretty common that they're shaped like this, right? They don't have a straight surface. And if I think about something sliding down this thing, and gravity pointing straight down, at every point along the way, I have different forces in the x and y direction, right? I have different magnitudes of forces in the x and the y direction, right? The normal force, if I can draw it well here, is changing direction the whole time, right? So the magnitude of forces on this block in each component direction is always changing. So that's one example of a system with changing forces. And now, let's think of another example. Let's think about a spring, okay? The spring was the example I used at the beginning, and we know if I depress it by some distance, and then I let it go, the force that it applies is different at every point along this journey, right? So let's imagine that I have my spring compressed by this distance x, okay? We know that the force that it applies is F equals minus kx, okay? And let's choose x hat this way. But if we think about the spring moving just some tiny difference, just a little infinitesimal difference, and we can say that the force of the spring equals minus kx for this little tiny distance, okay? And then we can say that the work done over this tiny distance is the force of the spring times dx, this little tiny distance, okay? And then we have an approximation for the work done. But then we could do it for the next little tiny distance, right? And for the next little tiny distance. And for the next little tiny distance, until we add them all up and we've done this whole distance x, okay? Each one doing a little tiny distance and making the approximation that we had a constant force over that little tiny distance. But if we keep increasing the number of steps out to an infinite number of steps, okay, and keep correspondingly decreasing the size of each step, that's the kind of thing that an integral describes, right? So the work is the force applied integrated over the distance. Okay? So now we have this integral for work, and this thing is a real relationship now. It's no longer an approximation once we make the step size essentially zero, okay, approaching zero, and the number of steps approaching infinity. Okay? And a similar kind of consideration would hold for a path along a curve. Okay? And the end result is that our work energy theorem and the idea of kinetic energy, it holds even for constantly changing forces. And this makes these tools really powerful for considering the physical world, okay? Because now I can look at things with constantly changing forces. And I can consider these things in a new way, okay? And I can consider systems that before I was just completely stymied by. So note that what wasn't important for any of the things that we discussed was time, okay? Work is done based on the distance that a force is applied. But remember our example from deadlifting versus Lasha performing the snatch in the homework? The difference there was kind of the speed that they did things at, right? So let's think specifically about the deadlift. In the deadlift, we have some weights, okay? And we lift them some distance off the ground, okay? Now, if I raise the bar some height, x, then the work that I do on the bar is equal to the force that I applied to the bar times x, okay? In the vertical direction, right? So this was actually F dot x. So if I'm raising the bar vertically, I'm only doing work for the portion of the force that's in the vertical direction, okay? And notice that I'm doing the same amount of work on it whether I lift it slowly or quickly. So if I pull it off the floor, I give it some acceleration. And of course, if I pull it harder, I'll give it a bigger acceleration, right? So it seems like I can change this force and change the work. But then for it to stop at the top, I must have decelerated it by the same amount, right? If it started from rest at the bottom, and then at the top here it's at rest again, then whatever acceleration I give it in the beginning, it has to have decelerated by the same amount by the time it gets to the top. Okay? That means that regardless of the speed that I impart on the bar, the total work done is the same. But often, we want to know how quickly work was done, okay? Not only how much work was done. And this brings in the concept of power. Power is the work done during some specific time interval divided by the length of that time interval, okay? So if we have joules for units of energy, right? The work done is units of joules, and that's per second, okay? And we call this unit W the watt. And watt, as we see, is joules per second. So it's a rate of work, okay? It's a rate of, in this case, changing the kinetic energy of the bar, okay? So if we think again about a person deadlifting versus Lasha Talahadze doing the snatch, that slow motion of the bar from just above your knees to about the height of your hips when you deadlift is a low power way of doing the amount of work needed to move the bar that distance x, okay? When Lasha was doing the snatch, in that case, we saw that what had to happen was he had to move the bar really, really quickly from, a little above his knees to about his hips. So that's a high power way of doing the amount of work needed to lift the barbell over that same distance. Okay? So the ideas in this lecture give us the concepts of work, kinetic energy, and power. And these concepts are powerful tools in our task of describing the physical world. We'll expand on these ideas in the next lecture and ultimately end up with a set of tools that will greatly increase the set of physical systems that we can consider and that will allow us to solve for some quantities in the systems that we already could model in much easier ways.